In this video, we're going to ask the question, is work positive, negative, or zero? So we're going to look at some different situations. First, I want to remind you that work is equal to force times the displacement. And if the force and the displacement are not in the same direction, then we do multiply it by cosine theta. So work is equal to FD cosine theta. That's it if it's at an angle. So first, let's take a look at a situation where the force is in the same direction that it's moving. So in the same direction as displacement. So if they are in the same direction, then we say that the force is doing positive work. Now let's say that the force is in the opposite direction that it's moving. So it's moving to the right, but the force is to the left. You might wonder, when might this happen? Well, maybe there is friction here. So the box, it was initially pushed, and now it's not pushed by the hand anymore. So it's just sliding and slowing down. The force is in the opposite direction that it's moving. So in this case, we have negative work. Now I want to take a moment to talk about what do we mean by positive and negative work. What does that mean? Because we understand that, okay, so positive work is when the force and displacement are in the same direction. Negative work is when the force and displacement are in opposite direction. But what does a positive or a negative work mean? So I want you to think about the energy in your system. So this circle here is representing the energy in our system. And when we have positive work, when there is force doing positive work on your system, then that means energy is going into the system. Okay. If the force is doing negative work on your system, then the energy is getting removed from your system. Okay, so in this case, energy is being added. Well, what kind of energy is being added to our system? Well, in this case, the object is going faster and faster, so it's gaining kinetic energy. In this case, it's slowing down, so it's losing kinetic energy. Now let's take a look at a situation where there is no displacement. So here is a wall, and you're pushing on this wall right here. Since the wall is not moving, since D equals 0, since the displacement is 0, the work done by this hand is also going to be 0. Okay. If there's no displacement, the work is going to be 0. Now let me show you another situation where the object is moving. So this object's moving to the right. So here's displacement, and the force is up. So perhaps it's connected to a string. Maybe a string is holding it up, but it's going sideways. If the force and displacement are perpendicular, then the work is also 0. Okay, so here are 4 cases of work. We have work that's positive when the force and displacement are in the same direction. Work is negative, force and displacement are opposite direction. Work is 0 when it's not moving, or work is 0 when the force is perpendicular 90 degrees to the displacement. Now, this is kind of an interesting situation here, because you might say, okay, so I have a string. So let's say I have a ball here, and I have a string, okay, that I'm holding the ball, and the ball is moving this way. So the ball is moving to the right, and I'm moving at constant speed. But you might say, well, but you could speed it up, right? You could speed it up. Now, what's going to happen if I move the string? If I go faster and faster and faster, and I speed this ball up? What happens is the ball, the rope is the string's gonna look like this, right? The string is gonna look at an angle. So if I go fast, it's gonna look like this. So if this is the force right here, here's the force, okay? So here's a question. Is this force doing work on this ball if it's moving towards the right and I'm pulling at an angle, right? So I'd like you to think about that for a moment, okay? Because is this force parallel to the displacement? Because it needs to be parallel to do work. Is it perpendicular? Because if it's perpendicular, it's 0. So the answer is that it depends on the component, okay? So this force at an angle is made up of 2 components. So I'm going to call this X component, and we'll call this Y component. So this X component of the force is doing work horizontally, but the Y component, which is perpendicular to the displacement, is not doing work, right? So this force at an angle is doing work through the horizontal component, but not doing work through the vertical component. Now I like to further analyze this and actually write out the work done by each of these components. Okay, so the work done by the horizontal component, the way we would write this would be the force, okay, the horizontal force times the displacement. And so this horizontal force times the displacement would give me the work horizontally. Vertically, oh, and also we can use a little trig. So if we know this angle, so let's say that we know what the angle here is, we can rewrite this as the work done by the x component of the force is going to be F cosine theta times d. Okay, so this is what it's saying is the horizontal component of the force is doing work. Okay, well, what about the vertical component? Well, the vertical component is not doing, of the force is not doing any work because the vertical component is perpendicular to the displacement. So that's not going to do any work on this object. Okay, now I like to go back to this problem right here on the right-hand side and analyze this a little bit. So I mentioned how in this problem, if the force is going up, so here is our force. The force is going up. We're moving to the right. There is no work done. Now, this might seem a little bit weird because if this force, let's say it's a tension force, okay, it seems like it should accelerate, right? Because you have a force here, but it's not accelerating. Well, if I were holding this object on a string, there's actually another force. There's another force, downward force, which is going to be Fg. So we have Fg right here. Okay. So in this case, the Ft is upwards and Fg is downward. Neither of them are doing any work. The net force is 0, and also the net work is also going to be 0. So the work here, whether it's the work done by the tension is going to be 0, the work done by gravity is also going to be 0, and we could say that the net work of those combined is also going to be 0. Now let's take a look at another problem where we have a box and we're moving this to the right. And let's say that there's friction. So we have an applied force, we have friction to the left, we have gravity force, Fg, and we have a normal force up. Okay, so in this case, let's assume that it's going at constant velocity, going to the right at constant velocity. So here is our displacement. Okay, so I like to go through each of these forces and think about the work that each of these are doing. So the applied force, is that doing a positive, negative, or 0 force? So the applied force is in the direction of displacement. So that's a positive work. Okay, it's doing positive work. The friction is in the opposite direction of the displacement. So that'd be negative work. The normal is perpendicular, so that is doing 0 work. And you write that down, so work is 0. And the gravitational force is doing 0 work as well. Okay, so what you'll notice here is that even though the applied force is doing positive work, because there's a frictional force that's doing the same amount of work but in the opposite direction, but it's a negative work, I should say, the net work done here is going to be 0. So assuming it's going at constant velocity, assuming a constant velocity, the net work, because we have a positive work and negative work, the net work is going to be 0, assuming it's going at constant velocity. Okay. If it's not going at constant velocity, if the applied force is greater than the friction force, then you're going to have a net of a positive work. All right. So my point here is to show you that each force is doing its own amount of work on the object, and you can look at those individually. You can also look at the net, the sum of the work that's done as well.